Hi everyone, we are Group 13 enrolled in Chemical Engineering at University of Waterloo. Our design project targets an ongoing concern for humanity, which is carbon emission control. In the hopes of mitigating carbon emission, we are optimizing a type of carbon capture and storage technology called chemical looping combustion, also known as CLC. CLC poses many benefits in improving thermal efficiency of combustion as it provides carbon capture in its intrinsic form. Overall, the project is to optimize a given model from our supervisor to observe the proximity of CLC commercialization while comparing it to the Vienna model. The optimization should abide by the financial and environmental incentives while meeting the power demand for the end users. Current design focuses on the following four major principles: hydrodynamics, mass balance, energy balance, heat transfer. Within these areas, the design focus will be determining the optimal operating conditions, process setup, and for direct measurables such as solid conversions and the input-output mass flow rates. Our design constraints are based on the proposed model to reiterate the working model to optimize. We will be operating at 1000 Kelvin and 10 bar with the most efficient oxygen carrier while meeting the health and safety protocols of CLC process. Also, the design model should output results that are aligned with the published literature data. The criteria for a successful project are to generate 100 megawatt of thermal power while achieving less than 15% of carbon monoxide and 5% hydrogen gas conversions. Essentially, it is in our aim to minimize the operational and capital cost of the process, followed by the decision matrix explained later. The published papers from various institutes have provided us a general understanding of chemical looping combustion. It involves an indirect combustion through oxidizing a metal to combust the fuel gas. In our case, ilmenite has been chosen as an oxygen carrier. For the operational unit, we are considering plug flow reactor for the gas phase and CSTR approach for the solid phase. The Intergovernmental Panel on Climate Change, the IPCC, and International Environmental Agency, the IEA, supports the necessity of CLC development in reducing the greenhouse gases.
Governing equations of each phenomena, which are hydrodynamics, mass balance, energy balance, and heat transfer, will be determined by fixing and unfixing the interconnected variables of the dynamics of the model. Optimization of the model will consist of constructing an objective function, which is minimization of the total operational cost, and various constraints to satisfy the design criteria, such as minimum acceptable purity and energy generation capacity. The ultimate goal for the project will be to assess the feasibility of the model with the below three possible design options when compared to the Vienna model. A decision matrix will be used to assess each design option based on different aspects of feasibility and allow the end user to make an informative decision on the best approach. The three design options presented are increase the height and the diameter of the reactor to assess if an industrial-scaled chemical looping combustion system is more feasible, or increase the inlet temperature for the fuel gas. The current model is conducted with an inlet fuel temperature of 800 degrees Celsius. A temperature threshold of 1200 degrees Celsius will be applied since the end product of ilmenite has a tendency of turning into pseudo-brookite at higher temperature, or increase the inlet air to fuel flow ratio to allow for more air into the system and less fuel gas relatively. The current model is conducted with an air-fuel ratio of 1.2. The decision matrix for alternative design options is illustrated here. As for the safety and environment aspect, the CLC process will first incorporate an inherently safer design with level indicators that will automatically shut off the system when deviations in some parameters have entered a predefined unsafe working range. For example, the temperature and pressure needs to be restricted below 1200 degrees Celsius and 50 bar respectively to avoid any unsafe operating conditions. The risk in each field is listed in a risk register table, and the effect of each risk is demonstrated. There are four main aspects of the risks, which are airflow risk, temperature risk, pressure risk, and condensing risk. Probability of occurrence and detection, as well as the severity, is assessed, and the risk score has been calculated based on the product of the three variables. Risk level is then evaluated based on the product: low for 1 to 3, medium for 4 to 6, and high for 7 to 12. The action that need to be taken in order to prevent the listed risk is then provided accordingly. For an environmental perspective, the CLC system takes an ilmenite particles as the oxygen carrier, which has a lifetime of 1,700 hours before a replacement is needed. Although the CLC system can further facilitate the carbon capture process to promote a zero carbon footprint, the waste of oxygen carriers is an inevitable byproduct in order for the process to work. A possible approach to address the issue will be to harvest the waste carrier and extract the titanium dioxide out for other commercial uses.
If the CLC technology can be commercialized, it has the potential to become an economically desirable climate change mitigation strategy. The project aims to develop and optimize a model that minimizes the total operational cost of the technology to study its feasibility. Once the model results fulfill the constraints and success criteria, the project will be considered achieved. To do so, each group member is assigned a module within the model: hydrodynamics, mass balance, energy balance, and heat transfer. The members will conduct literature review and develop their respective modules. The engineering tools used for the model is the Pyomo library in Python. Pyomo is a software package that is used to formulate optimization models. It supports the IPOPT nonlinear solver that can solve the complex phenomena in the CLC system. Pyomo is selected over other well-known software like MATLAB and COMSOL due to its superior optimization capabilities. While the other packages excel in modeling complex systems, Pyomo eclipses them in terms of flexibility in formulating and solving optimization problems. Once all the modules are developed, they will be combined into a single model. The optimization of the cost will be done by sweeping through various values of inlet air-to-fuel flow ratios. Finally, the results will be validated with the published experimental data.
To sum up, we have thoroughly examined the 4 module pillars that make up the project: hydrodynamics, mass transfer, energy balance, and heat transfer, and their interdependent relationship with each other. All equations involved within each module are listed with clear identification with the input required from other modules and the output generated after running the module, as well as a clear expectation of how each profile behaves and how each module is being applied within the combustion loop. Thorough validations have been conducted on the preliminary model in place to locate for possible source of error. Currently, 3 parts within the module have been identified to contain certain source of error. However, how much each error contributes to deviating the model from literature data will still need to be further investigated. 3 errors identified so far are hydrodynamic profiles within the fuel reactor that is not properly being set up to describe the actual situation. Second, incorrect heat loss model that shows the total amount of heat loss approaches 0 with an increase in insulation thickness when it should approach a set value bigger than 0. Third, improper use of heat transfer correlation when determining the cluster phase heat transfer phenomenon. So the next step for us will be to correct all 3 errors as below. First, re-establish the hydrodynamic profile to better match the Vienna model setup and adjust the pressure drop profile since this is the backbone of our model. Second, correct heat loss transfer model to determine the relationship imposed onto heat loss versus the thickness of insulation. Last, cross-reference heat transfer model literature correlation and test each one to assess the validity of each and update the model accordingly.
So, that is the end of our presentation. We are hoping to gain personal knowledge as well as make a meaningful contribution to the world with this design project. Thank you all for listening. The references that are associated with the literature review are located here.